Alright, so let's get started then with a short introduction and a review of some fundamental material that we're going to need for chapter 4. So, in the lateral directional sense, we now have a lateral force, a roll moment and a yaw moment. So if we take a look at figure 4.1 from the textbook, page 136, here's our lateral force look, positive in the positive y-s direction out the right wing, remember. A roll moment about the x-s axis, which has notation L sub a, and also a yawing moment about the z-s axis, which is given the notation N sub a. So we've seen that in our modelling of longitudinal forces and moments, we dealt with the symmetric control surfaces, right, that affected the aircraft in the longitudinal sense. So we looked at the elevator, we also had a look at stabilators, which were the fully movable horizontal tails, and also stuff like flaps are included in those symmetric control surfaces as well. So now, when modelling the lateral directional forces and moments, we need to consider the asymmetric control surfaces. So here we have ailerons and the rudder, of course. And now we introduce these two new pieces of notation, delta sub A and delta sub R, to denote the inclination angles or the deflection angles of the ailerons and the rudder, in the same way as that we use delta sub E to denote the inclination angle of the elevator. So we saw in the previous chapter then that the angle of attack was used to model the longitudinal forces and moments, right? So now, because we're dealing with lateral directional forces and moments, we're going to need to model based on the angle of side slip, beta, okay? And the convention is that beta is positive when the airflow hits the nose from the right hand side. And I can't remember whether I've introduced this notation before, ALF, for aft looking forward, right? So aft looking forward, side slip is hitting the nose of the aircraft from the right hand side, so that's positive beta, okay? A couple of other bits. Dihedral, so this is going to be important when we look at what's affecting the side force on the aircraft. So if the aircraft has large positive or negative dihedral, or anhedral in the negative sense, then the component of side force due to side slip is going to be larger than if it's got no dihedral, right? So that just tidies up that little bit of notation. And also, prop wash, hope you like my little picture there, I was quite proud of that. Prop wash can also contribute to the lateral force on the vertical tail, or the side force on the vertical tail, which can induce a yawing moment. So one final thing to discuss here is this concept of sidewash. So, oh, and by the way, I'm on the lime cucumber Gatorade today, which of course is the second best Gatorade flavour after the green apple one. So this sidewash effect then, we saw in the previous chapter when we were dealing with longitudinal forces and moments that angle of attack could be affected by the interaction of the wing and therefore change the effective angle of attack onto the horizontal tail. We called this downwash effect epsilon. And we have a similar effect in the lateral sense, right? So the angle of side slip could be affected by what we're going to call sidewash sigma. So we say that the angle of side slip on the horizontal and vertical tail is essentially the free stream side slip angle minus the effect due to sidewash, and that's just a function of beta, right? So again, as we did in the last chapter, we can just apply a Taylor series expansion of sigma about this reference condition. So the sidewash effect is 0 when beta is 0 to get this expression here. And typically the sidewash effect is much smaller than the downwash effect. So one final thing to discuss here is the potential differences in vertical tail design. So in this first diagram here, this represents what's known as a conventional vertical tail design, and you can see that typically the rudder position sits high enough up the vertical tail as to be outside of the wake of the horizontal tail, and that allows full control surface effectiveness because it's getting as close to the free stream flow as possible. The next possible design is what's called a V-tail. So instead of having one vertical and one horizontal tail, a V-tail tends to have two vertical pieces that go off at an angle. And basically they have rudders basically, but they're operating in two planes now, right, because of the angle of the tail. So the control surfaces on these pieces of the vertical tail combine the effects of the conventional rudder and elevator, and they're often referred to as ruddervators. Finally then, our aircraft might not have a vertical tail at all, in which case it relies on the ailerons to provide the side force. So in this example here, I've used the example of the X-47B, the unmanned combat aircraft. If you're not familiar with it, go and look it up. It's got folding wings, but the wings critically have this very high trailing edge sweep angle, which means that when you deploy the ailerons, you get some side force. And so the ailerons in this particular case do the job of conventional ailerons plus the rudder combined, right? So that's why a vertical tail is not necessary for a highly swept trailing edge wing.